So I'm Seth Redmore, and I'm with a company called Lexalytics, and what I'm going to talk about is how we took an algorithm that was and process for doing online movie recommendations, stuff that was developed around the time of the Netflix challenge, and how we turned that into a very efficient, very scalable, multilingual syntax parser. So what are we actually going to talk about? Who we are, who I am, who we are. Syntax, semantics, and context. So we're going to start kind of high level. Talk a little bit about syntax parsing and some of the ambiguities that we as humans just kind of naturally deal with, but that machines are going to be way less good at dealing with. How you can apply matrices to resolve some of these ambiguities based on large, unsupervised training sets. Switch out a little bit and say, okay, let's talk about movie recommendations and matrix factorization and movie recommendations, how that actually works. And then say, okay, here's how we applied it to syntax parsing, how we actually trained this, and sort of where we're going with it, and some of the high-level results we got with this. Lexalytics, founded in 2003. We've been around for a while. We build the text analytics engine. We provide it as on-premise software or as software as a service. We are very popular in social listening platforms, so a lot of the major, if you pick the top 10, probably 6 or 7 of them use us. For social listening, for customer experience management. Then we've got onesie-twosie customers in like pharmaceuticals, business intelligence, things like that. We process a lot of content. So let's talk about syntax, semantics, and context. So each of these is important for understanding the meaning of a sentence. And so syntax is your actual structure. Semantics is the meaning of the individual words. There's better definitions than this, but bear with me on that. And context is way fluffier. So, so it could include the shared history between whoever's speaking and the person they're speaking to. It could include, if you just see a tweet that says, I love the Apple Store. Okay, prima facie, just by itself, all you can say is that that person loves the Apple Store. But if you know that the last tweet was, I waited in line for 3 hours and the genius was an idiot, then that tweet means something very different. So we've done a lot around semantics, been a lot around syntax. One of the things I think we're going to be seeing a lot more, this is a side note, over the coming years is involving a context. Because there's certain problems that you really need the context in order to solve. I believe that sarcasm and irony are very context-dependent problems and require that. And so I think you'll see a lot more with tracking individual context or clustering users into contextual groups. But we're going to focus on syntax today because that's the title of my talk. So syntax, we've all done these. It's funny, my mom's an English teacher, and I actually had her for English in high school. And it's, so sentence diagrams, it's just like, I'm looking at doing these, and I'm like, I'm never, ever, ever going to use this again in my entire life. And so now my career depends on it, and it's just my mom finds it really, really funny. So you have to be able to tear these sentences apart and associate things. And dependency parsing is expensive. It's computationally expensive. There are different ways to do it that are less computationally expensive, and we're going to be talking about one of those ways. It's really important though. So if you look at this sentence, it's ambiguous towards tea, positive towards coffee, but if you were to parse this incorrectly, this is the correct parse, but if you don't want to have the not apply to prefer, you don't want to just pull out don't like tea, because it's not that I don't like tea. So these are all syntactical things that affect the overall meaning of the sentence. And so you have to be able to understand the structure of the whole sentence in order to understand what's going on. So let's take a little more ambiguous sentence. So Jane will be joining a team already with the search expert. So this tells us a couple things if we can understand the meaning of this. It tells us maybe there's a concern about the fact that there's a lot of search experience already on the team. There's already a search expert there. Why is Jane joining this team? Right? So there's some stuff that's implicit to this sentence that you get with the fact that they're saying already with a search expert. And so understanding this gives us a meaning. This is where we started to get into more ambiguity. So Jane is joining a team already with some search experience. Is Jane the one with some search experience, or is the team with some search experience? And this is the sort of ambiguity that we tend to deal with really well as humans. And so we would just say, okay, Jane is joining, and she's got some search experience, right? If you look back, this sentence is also equally ambiguous, but we would tend to resolve it a lot faster. Jane may be carrying around a search expert with her, like in her backpack. And that's an unlikely parse, and we know that from, from how the world looks to us, that probably not carrying a search expert around with her, maybe, but machines don't know this. And so that's what we're trying to solve, or solved, is the problem with how can you figure out these linkages inside of the sentence and the dependencies. So let's step back for a second and say, how could we actually approach this problem? So first we would take a sentence, lots of them. Part of speech, tag them, chunk them. And so, part of speech assigns individual noun, verb. Chunk assigns what kind of phrase it is, as well as, okay, these words belong together. And then we use certain rules to say, okay, well, this one almost certainly isn't going to modify this other one. So for example, a conjunction is going to modify things of two types. You aren't going to say I ran and Bob. So you can use these rules to kind of prune things a little bit. And then you end up with a tree of possible links. So pause, tag it, chunk it, and then the different chunks here, Jane will be joining a team already has search experience, will be joining already has search experience, Jane already with search experience. So these things you put together, and you can use this as a training set across a sufficiently large corpus of content. And so what you end up with is you end up with a matrix, okay? And so your matrix is all of the chunks and how they relate to each other, okay? This is large and it's brittle, but you can see how this could be used to resolve those questions about, okay, what are the proper links? Because over a large enough set of content, you will start to see similar links emerge. Let's talk about kind of how big this problem is and trade-offs between size and performance, much like a spork. So the Netflix data set was about 100 million triplets. Our training data set is about 40 gigs of English text, about 500 million sentences. Once we do the pruning that I talked about before, it makes the problem more tractable because you drop it down, but you still end up with about 200,000 chunks. And so you're looking at a matrix of 200,000 by 200,000, or 40 billion cells in the matrix. That's a lot to carry in memory, and it's very brittle. So the problem here is, if you just look at the exact matches inside of the sentences, then your matrix isn't going to be able to handle matches that aren't quite like that. And so what you want to do is you want to extract some sort of latent factors among these that allow you to say, okay, these are similar to this and that's similar to that. And so, okay, this is probably going to match right. And you also want to be, so how can you compress it so it's not 200,000 by 200,000? And how can you extract these latent factors? Movie recommendations use collab. So stepping back, hold on a second. Sorry. And I even quit smoking a while ago. So consider the problem of recommending movies and say, okay, here's my matrix of movies versus users. So users and movies. And some users are going to rate more movies than others. And you want to be able to say, okay, for the user that hasn't rated a particular movie, if they want to watch this movie, what is the rating for that particular user for that movie? There's a couple different ways to do this. Nearest neighbor approaches were sort of the start of this and kind of the most intuitive approach, which is basically looking for somebody that looks like me. The problem is these are very sparse matrices. So you have 20,000 movies, you have 100,000 users, and each user is only, say, rating 200. It was actually, this is true. So they were only rating an average of 200 movies. And then you have some users that rate 2, and then there was this one user that rated 17,000 movies. Okay, it's like, okay. Did you watch them? So using a nearest neighbor approach fails because of the sparseness here. So what you want to be able to do is extract the latent features in the movies to say, okay, this one is kind of like this one, and so I can make some guesses about what's going to be inside of the blank columns. So let's talk a little bit about what that means. So For matrix factorization, what you're trying to do is split this big matrix of users times movies into two separate matrices that are each size of, say, the users times a number of factors and the movies times a number of factors. Okay, so the number of factors is going to be smaller than, say, the users and the movies. So say you have 10,000 users and 10,000 movies. If you can get it to like 10,000 users and 10 user factors and 10,000 movies and 10 movie factors, you've really compressed the amount of space you have to worry about. And you can find some similarities across these things. And so basically what you're trying to do is find k number of latent features so that you have two separate matrices, so that the dot product of these two matrices allows you to give an approximation of what should be in any empty cell. So you want to find these matrices. You have to actually learn these factors. And I'll talk a bit about how we actually approached it. So what you want to do is minimize the error, the least squares error, on the cells that you know. And so there's other things you want to do to prevent overfitting of your models. So there's regularization and things like that that you want to do that I'll touch on briefly. But if you sort of look at this as, broadly speaking, this is how you deal with matrices. And then there's a couple papers I refer to that if you want to get really deep into it, you can. So in our case, we ended up doing 200 factors for ours. And so it ended up going from 200,000 times 200,000 to 200,000 times 400. So we go from 40 billion to 80 million. Great. OK, so there's a certain amount of compression. And we ended up at 200 because we tried 100, and we tried 400, and we tried, and sort of worked our way experimentally up to that. A lot of this is try it and see, and try it and see, and try it and see. There wasn't a particular law that we could follow that said, OK, it's going to be n minus 2 divided by x. It just wasn't. We just had to try it. This is the really cool part. Hashing. So this graph that isn't terribly readable, it's right out of this paper. So I think I'll post this up on our blog later, so you can actually get to this MIT paper, and it talks about hashing and matrix factorization and efficiency around it. But what this did was, so this particular use case was around each movie data set. It was a rating from 1 to 5, not 1 to 4, so it was 1 to 5 ratings. And then the scale is the root mean square error, or MSE error, for the amount of compression from hashing. Okay? So by hashing, basically, you are randomly assigning any particular entry into one of the entries inside of the hash table. And so if you look on the left, thousands of entries, elements in U, so the user matrix, they go from about 1.2 million down to 60 million, and then thousands of elements in the movie elements, from 32,000 to 5,000. So we're talking a factor of 20 compression on the left, and a factor of something like 7 or 8 compression. And they went from a 1.2 root mean squared error to a 1.3, which is crazy, right? That you're getting a 20 to 1 compression, times more than 20 to 1 compression, and you're only losing that much in terms of your recall. So we actually did 50% compression of phrases, and it cost us 3 points on our F1 to do that. We have a lot of trade-offs we have to make because our customers are sensitive to how many cores they have to throw at a problem. If they're dealing with the Twitter fire hose, if they're dealing with very large documents, if they have latency requirements in terms of alerting. And the big issue is it isn't sort of, OK, if I could spread all my content evenly like peanut butter over the bread during the day. The problem is when they get this big burst because something happened. And so they need to be able to chew down through those because they've got a 30-second window in which to alert their customers that something has happened. So we have to make trade-offs all the time between accuracy and performance. And this was a great trade-off for us. So it really increases our number of cache hits. All that sort of stuff just works better. So how do we train this? There's a lot of, this is where the embracing the noise comes in. We start out with extracting all of those chunks, and then we randomize them, we mix them up. And so then we hash the input phrases. So the first thing, after we mix them up, we hash everything. And so we tried a couple different seeds and stuff, so we optimized that a little bit. And then you randomly initialize both matrices. So there's another bit of randomness. And then what you do is apply a model fitting algorithm. So for matrix factorization, there's a couple different model fitting algorithms that are popular. Stochastic gradient descent and alternating least squares are the two that you're going to see most commonly here. In our reading and our research, we decided to go with ALS. There's some certain performance characteristics that are superior for us in our case. Some people prefer to go with stochastic gradient descent. It's really kind of up to you. Sometimes the ALS will diverge, and so there's some potential issues with it, but we just throw it away if it diverges. So does the model converge once you've actually gotten to it? No, if it's diverging, okay, great, throw it away, start again. Hash your input phrases, randomly initialize both matrices, and go. Did we get a better F1? So we had a set of content that we were scoring that we knew how it behaved, and so we just score the new matrix against it. Did we do better? Okay, great. So we'll throw away the last one and keep this one. And then are you bored with actually doing this process, or are you getting limited returns? And so it really came down to, okay, we just hit a point where we just really weren't getting anything worth spending the 3 or 4 days of computer time to run the model. We had to run through this about 300 times before we actually got something that we felt was a good local minima of performance. Local minima in terms of the noise, local maxima in terms of performance. And this is really an important part of this kind of factorization is you're starting out with a number of random things. And sometimes the distribution is going to be a pathological distribution, and it's not going to converge right. And that's OK. It's nobody died. It's just you throw it away and you do it again. And you just keep doing it until you reach the point where it's like, OK, I'm not getting any further. There's a couple details about this. I already talked about the ALS versus stochastic gradient. When you are looking at model fitting here, there's a couple things that you need to consider, and I'm not going to spend a bunch of time on this, but feel free. There's all kinds of literature about this. How do you change? Okay, so there's a value in a cell, and your error is this far away. How can you move closer to that without sort of overshooting it? How can you make big jumps in the beginning and then small jumps later as you get closer? So the loss functions are all about how do you actually move closer to the value you're actually looking at based on your error from there. And so we went with something called Huber's robust loss. There's other error functions you can use. We tried them. They didn't make a huge difference. There were small differences. And so this one just happened to have some good characteristics in terms of how it behaved early on and then closer on. Other things with matrix fitting is content that comes in earlier means more than content that comes in later. So it's sort of a square of how far in you are. And so big changes are going to happen early on and then smaller changes later on. Regularization is another concept you'll see. So regularization is a way to kind of keep things from getting really weird inside of the matrix and prevent overfitting. Because if you fit too hard to the stuff that's there, you could end up with something that's complete noise. And but it matches really great there, but it's some really complicated fitting that's not going to predict anything in the future. And so all the regularization parameters help prevent that. So backing up, consider this problem. Do you want me to get anything else while I go to the store for milk? Pause tag it and chunk it. So here's the possible lengths, right? And the interesting chunks inside of here that that I want to talk about to the store for milk. So is it a milk store, right? And we can tell that it's not. He's going for milk, right? I mean, we know this. And with a large enough corpus of content, if there were milk stores, you would see, milk stores closed today in observance of this holiday, and milk store robbed yesterday at 5 p.m., and store for milk closes down and lays off all the employees. So that's what the unsupervised learning across a large bunch of content does. So we used, for ours, we used Common Crawl, Wikipedia, social, and a bunch of big news corpus. And these things just pop up, and it makes more sense. So results, we reduced our polar opposite error. These are errors where we see, we have a set of content that's really hard content. We picked it, hand-curated it to make it really hard for ourselves. So the polar opposite errors inside there, we reduced by 50%. So stuff that was scored positive should be scored negative. Our worst case entity sentiment F1. So whenever people talk about accuracy in text mining, you always have to ask the question, okay, over what content set? And how are you measuring, how are you measuring against it? What's your inter-rater agreement? All that stuff. So I'm just talking worst case, we got a 10% improvement in our F1 scores. These are the kind of things that we handle way better now. CNN reports that Indiana is facing an unpleasant backlash. Indiana, negative, CNN, neutral. Bob's House of Donuts, stop making bad donuts. Well, that actually is positive inside of here. But Rachel, stop playing on time, is neutral. So that's what we did. That's how we did it. And now we're on to questions, if you have them. Thank you for listening. Yes?
So I missed what those numbers were in the chunking matrix department.
Which numbers, or where?
In the matrix you showed at the beginning.
Back here? So stop me when, this one? Yeah. So this is for a set of, for a corpus of content, we'll see the word team with, is joining 22 times, will be joining 10 times. I mean, it's a lot more complicated than that under the covers, but that just gives you a general idea of if you process through stuff, you're going to naturally see chunks occur with each other and chunks link to each other. And if you look over a large enough corpus of content, rare cases will get mushed out. And the common cases will, so you can say, oh, it's probably going to be linked with this. So the way to think about this is like this. I threw the ball, right? Things that you throw, relatively small, you can hold in your hand. Chair is probably starting to get to the upper limit of things you throw. You don't throw a mountain. So you're never going to see I threw the mountain or I threw the building unless you're talking about Legos. So that's how these things line up. So the properties of things that are throwable, you'll start to see them kind of line up inside of the matrix. Through comes with things. Walk goes with certain things and stuff. And it's not just noun-verb relationships, it's others. But does that answer your question?
Yeah.
Okay.
And then we use some rules to map, you have these, I guess, relevances, but then we use some rules to using the product speech tags to make the actual links.
So the pause tagging makes the matrix in the first place. So, and then we use the matrix factorization to determine, okay, what are the things that are most likely to go with other things? And then we use that to help us understand, okay, what are the links inside of a sentence? And so we pause tag first, and then we chunk into the chunks, and then we this is called the chunk parser. And so then we use the chunks, and then we use this syntax matrix to actually say, oh, okay, that chunk probably goes with this other chunk.
Because I mean, two words could appear together, but they could both link to, they could have links to the verb that shows up in the sentence, but not to each other, right?
Sure. And when we parse an individual sentence and we do the pause tagging, the chunking will handle a big part of that. It's the relationship between the chunks that we're worried about with this.
I think you guys can take it offline.
Yeah.
The next up is in 4 minutes.
Okay.
Thank you very much.